Hello, welcome to my talk all about fluid. This talk is on Euler Equation. In this talk, I will show you what is the difference between the Eulerian and the Lagrangian representations for describing fluid motion, and how Euler Equation and the fluid dynamic equation in the Lagrangian representation are derived. I will also make a comparison for fluid dynamics equation and the solid dynamic equation, which could help you to better understand the issue with fluid dynamics equation. In principle, there are two different ways for describing fluid motion and state: Eulerian and Lagrangian representations. Eulerian representation examines the fluid motion at the fixed position in the fluid domain, and thus the parameters of interest for fluid motion and state include velocity vector, pressure, density, and etc. And all these parameters are the functions of the independent spatial variables x, y, and z, and time t. A different approach is the Lagrangian representation, for which the individual particle or fluid element are traced over time, so we can see clearly how the fluid particles moving around in the fluid domain. In such an approach, particles' position can be determined by its coordinates xt, yt, and zt. However, on the particle trajectories, x, y, and z are not independent variables, which is the main reason why establishing the fluid dynamic equation in such an approach is very difficult and even impossible today for 3D viscous fluid dynamic equation in the Lagrangian representations. In such a representation, the independent spatial variables for the specific particle are its initial position, at0, bt0, and ct0, or sometimes it is called the particle identity. In this slide, I will show you the physical meanings of these two fluid motion representations. In the Eulerian representation, we can focus our attention to the fixed positions, such as the flow around the small island in the video. In this particular case, the overall flow pattern are not changing too much with time, especially the upstream of the small island. Imagine we take a snapshot of the flow as we see in the picture, which could be the flow that the Eulerian representation describes. In the Lagrangian representation, we can focus our attention to the forms on the flow surface. These forms follow the flow particles and move from upstream to downstream. We can see the different velocity of the fluid particles along the trajectories. If we have a lot of such forms, we can see the flow better. Here, an analogue is made for the Eulerian and Lagrangian representations. Suppose you are in a Formula 1 car race. As a general fan of Formula 1 car, you may put your attention at the finishing line and see how fast each car passing the line. This is very similar to the Eulerian description of the fluid motion. If you are a fan of a specific car or driver, you would like to chase the car all the time on the track. However, you may need special equipment to overlook the whole track, so that you can chase the car all the time, which is similar to the Lagrangian representation for describing the fluid motion. A similarity can be seen in some football matches, in which all players on the pitch are traced in the play, and then it is possible to calculate how long a distance each player has run. For fluid dynamics, Eulerian representation is mostly employed. The corresponding fluid dynamics equation has been well established. In contrast, the concept of Lagrangian representation seems simpler, but the corresponding dynamic equation for fluid in such an approach is much more complicated. In the Eulerian representation, it is convenient to divide the fluid domain into many small elements, all fixed in the places. For a good illustration, cubes are most used, as seen in the figure. In the Eulerian approach, the parameters of interest for fluid motion and state include fluid velocity vector, pressure, density, temperature, etc. While in the Eulerian approach, the actual position of the fluid particles might not be very important in many practical applications. A very important concept for fluid dynamics in the Eulerian approach is the substantial or material derivative. This special derivative was formerly employed by Euler when he derived the Bernoulli equation or Euler equation. When we look at the fluid motion and state at the point in the fluid domain, it can be seen that the parameters of interest would be the functions of the variables x, y, z, and t, such as velocity vector, which is the function of the spatial variables x, y, z, and t. And in such an approach, the spatial variables x, y, and z are independent. As such, the fluid acceleration can be naturally calculated using the chain rule. Take the velocity component u as the example. Acceleration can be calculated as this, where the capital D means the substantial derivative. In a more compact form, it is written as this, and for the 4 fluid acceleration vector, we have the form like this. As a result of this, for fluid dynamics, the substantial or material derivative must be used. The concept of the substantial derivative is still very confusing to many of us. One question would be why we can use the normal derivative in solid dynamics, but we have to use the substantial derivative in fluid dynamics. In this slide, the physical meaning of the substantial derivative is explained. Let's look at the fluid acceleration. We can see the substantial derivative consists of 2 main parts. The first part is called the local acceleration, which can be imagined at the specific point P in the fluid domain. The local acceleration is due to the change of the velocity at this point in a time interval delta t. In a steady flow, this acceleration term vanishes. The second part of the substantial derivative of the fluid acceleration is called convective acceleration. This convective acceleration is caused due to the combination of the velocity spatial change and the relative velocity component. For instance, in a steady flow in a long uniform pipe, there is no convective acceleration. However, if the pipe has a contraction, there will be convective acceleration in the flow. The reason for the difference between the fluid motion and the solid motion is because the fluid motion could not only have the translational and the rotational motion as the solid, but also the flowing motion. And it is the fluid flowing which causes the convective acceleration. For the fluid dynamics, the continuity equation is part of fluid dynamics equation, either Euler equation or Navier-Stokes equation. Hence, it will be derived here first. Consider a fluid element, a small cube in the figure. Take the y direction as an example. At the interval delta t, some fluid mass flows into the cube from the left vertical plane at a flow rate no v, and at the same time, some fluid mass flows out of the cube from the right vertical plane at a flow rate no v plus the partial differential of no v with regard to y times delta y. The mass increment in the cube in the time interval is the difference between the flowing mass less the flow out mass. Hence, it is calculated as this. In a similar manner, the mass increment can be calculated in the x direction and the z direction. The total mass increment in the cube in the time interval delta t is the sum of the mass increment in all three directions around the x, y, and z axis. In the same time, for the given cube, the mass increment means proportional increment in the fluid density. Thus, we have the equation as this. Put these two equations together, we can have the equation for the fluid mass conservation, or the continuity equation. It should be noted that the density derivative with regard to time has been taken as the partial differentiation here. It is because the corresponding density change is only purely due to time, while the density's spatial change has been included in the other term. Now we can look at the moment equation for fluid motion. For the fluid moment, the forces acting on it can be separated to two different types of the forces, the body force and the surface force. The body force acting on the element is proportional to the fluid volume. It is calculated as this. For instance, the fluid gravitational force is a one body force for the fluid. For a simple illustration, we take the surface force in one direction as an example. For the element, the pressure force acting on the left vertical plane has a direction with the y-axis, while the pressure force acting on the right vertical plane has a direction against the y-axis. Hence, the net surface force in y direction due to the pressure is calculated as this. And then we can establish the dynamic equation for the fluid element. Here, the Cauchy moment equation is used. the Cauchy moment equation was actually derived from the Newton's second law of the motion. Here we can see in the Cauchy moment equation, the force density is used here from the body force and the pressure. And also we can see the substantial derivative is used in the equation. However, it should be noted that the substantial derivative cannot be used directly to the Newton's second law of the motion. An explain might be referred to a journal article in 2005. It is reported the mass transfer velocity in here is different from that of the fluid particle motion in compressible flow. Apply the detailed substantial derivative. The dynamic equation can be written as this. Similarly, we can have the dynamic equations in x and z direction as this. In a vector form, the fluid dynamic equation can be written as this. This is actually the Euler equation in vector form. We can also use the Einstein summation for the Euler equation. Here, a comment should be made for the Cauchy moment equation. The Cauchy moment equation for fluid dynamics is the same regardless whether the fluid is compressible or not. So, the fluid compressibility is only represented in the continuity equation, where the fluid density is not a constant there. Bernoulli's equation is a very useful equation and has many important practical applications. The most useful Bernoulli's equation have a very simple form, as we can see in many textbooks. It is well known that the Bernoulli's equation is actually an integral form of Euler equation under the hypothesis of a steady flow. The Bernoulli's equation is valid for the inviscid flow in a general form. This is the same requirement as for Euler equation. For a steady flow, we have the equation as this, and the body force must be conservative. For instance, the gravitational force is a conservative force. Here, the vector calculus identity is used. Lastly, the correct Bernoulli's equation has one more condition. Either on the fluid streamlines, the above equation can be written as this. So on the streamlines, the last term is 0 because the cross product of the core of velocity and the velocity vector is perpendicular to the velocity vector, while the vector ds has the same direction as the velocity. So the last term is 0. Or if the flow is irrotational, the core of the velocity is 0. Under these conditions, we can have the Bernoulli's equation. For a simple application of the Bernoulli's equation, for the examples in the figure, we can take the tank bottom as a reference height, for which z would be a constant in the Bernoulli's equation. So, for the pressure P0, P1, P2 will be all reference to the water tank bottom. In the water tank, the velocity V0 is very small, hence the water level H0 is high. In the large pipe, the flow velocity is larger than V0. Hence, its corresponding water level H1 is lower. In the small pipe, the flow velocity is largest, so its water level H2 is lowest. Therefore, this experiment setup explains the Bernoulli's principle very well. The pressure decreases when the flow speed increases. The second application of the Bernoulli's equation is for the Pitot tube. Pitot tube has been and still is very useful instrument for measuring fluid velocity. This is especially true before LDV and PIV were not so popular for measuring fluid field. But the LDV and PIV might be more suitable in laboratory conditions. In engineering environments, Pitot tube is still widely used. There is an interesting story for Pitot tube. Only Pitot invented the device in 1732, which was well before Bernoulli's principle 1738 and Bernoulli's equation 1752. However, Pitot showed the Pitot tube could measure the fluid velocity, but the theory behind it was not very clear at all. More than 100 years later, in 1856, only Darcy worked to improve Pitot tube design, which becomes a form very similar to the modern Pitot tube we are using today, but the Bernoulli's equation was not linked to the tube yet until 1913, when Professor John Airy of the University of Michigan first used the Bernoulli's equation to establish the theory for Pitot tube. In the figure, it shows the Pitot tube measures the total pressure P1 at the front of the Pitot tube and the static pressure P0 at the side of the Pitot tube. When the Pitot tube is placed with its head directly pointing to the incoming flow, as seen in the figure, the measured pressure P1 is the total pressure of the static pressure P0 and the dynamic pressure. Use the pressure difference between the total pressure and the static pressure, and the fluid velocity can be easily calculated. Here is a picture for a real Pitot tube, which is a Pitot tube used on an airplane. Bernoulli's equation and Bernoulli's principle are widely used in practical application. The very famous one would be the flow passing through the airfoils or wing of an airplane. When the flow passes over the wing or airfoil, a high-speed flow and a low-speed flow are created. Thus, low pressure and high pressure are produced on the up and lower surfaces of the wing, which create a lift to support the airplane flying in the air. Another good example is the Formula One race car. In racing, a high-speed airflow would pass the underbody of the car. Based on the Bernoulli's principle or equation, a very low pressure is created underbody, which would suck the car to the ground of the track, which is very important to keep the car racing at a high speed on the track, especially in tuning. Now we will take some time to study the Lagrangian representation. This is mainly for purpose of a comparison between the Eulerian and the Lagrangian methods. It is also important if a comparison of fluid dynamics equation and the solid dynamic equation are compared. Consider the fluid element or particle, which is similar to a mass point. Its dynamic equation, Lagrangian approach, can be simply expressed as this. Superficially, the dynamic equation in the Lagrangian representation seems simpler than that in Eulerian method, since there is no nonlinear convection term in the acceleration. However, when we calculate the force on the particle due to the fluid pressure, the problem becomes very complicated, since in the Lagrangian approach, x, y, and z are not independent variables. For establishing the dynamic equation in the Lagrangian approach, the force due to the pressure are transformed using the independent spatial variables for the particle A, B, and C. Applying the chain rule, we have the equation as this. After some mathematical deductions, we can obtain the fluid dynamic equations in Lagrangian approach. So you can see the fluid dynamic equation in the Lagrangian approach is much more complicated than that in Eulerian approach. According to Horace Lamb, both Euler equation and the fluid dynamic equation in the Lagrangian representation were both derived by Euler. And it should be noted, the four fluid dynamic equation in the Lagrangian representation has not been derived yet, according to Andrew Bennett in his book Lagrangian Fluid Dynamics. The problem remains open in 3 dimensions. In this slide, the fluid dynamic equation and the solid dynamic equation is compared. When we compare the dynamic equation, it can be easily seen for fluid dynamic equation, the substantial derivative for the acceleration must be used. But for the solid motion, only the normal derivative is used. But why we have to use the substantial derivative in fluid dynamics? In solids, we can only use the normal derivative. The answer is, in studying the motion of a solid, the Lagrangian representation is automatically applied. If we use the same dynamic equation for the solid, but without the surface force due to the pressure, we have the equation as this. Multiply the mass m equals no v to the above equations. We can have the dynamic equations for the solid dynamics. This equation is the same as this because the spatial variables x, y, z are only the function of time t. These equations are exactly the same as the Newton's second law of motion. This explains why we do not use the substantial derivative for solid dynamics.